Hello, and welcome to the Breakthrough Podcast, the podcast where we dive deep into innovative STEM solutions to real-world problems that will shape our future. I'm Drew, and today we will embark on a journey into the fascinating world of piezoelectricity. Piezoelectricity might sound complex, but it's actually a fascinating phenomenon powering some of the most exciting innovations today. It's the science of converting everyday movements, like walking or typing, into usable electricity, which could soon keep your smartphone, Fitbit, and other devices charged without ever needing to plug in. In today's episode, we'll break down what piezoelectricity really is, explore how it works at both the atomic and practical levels, and check out some of the most exciting innovations turning movement into usable electricity. We'll also examine the challenges that scientists and engineers face, as well as what the future might hold for this green, sustainable technology. Let's start by unraveling the word itself. Piezoelectricity. It's derived from the Greek word piezo, meaning to press or to squeeze, combined with electricity. In essence, it refers to the ability of certain materials to generate an electrical charge when they are physically stressed, like being squeezed, bent, or vibrated. To get a little more scientific, piezoelectricity is a property of some crystalline materials, where mechanical stress causes a displacement of electric charges within their structure. If that sounds complicated, think of it like this. Imagine a sponge full of water. When you squeeze the sponge, it compresses and forces water to come out. Similarly, when you squeeze, bend, or push on certain materials, they'll force out a small flow of electricity. Some common piezoelectric materials include quartz crystals and lead zirconate titanate, otherwise known as PZT. More recently, scientists have been developing flexible piezoelectric polymers. These polymers are the most useful piezoelectric materials because of their controllable size and flexibility, which allows engineers to develop powerful wearable technologies. While piezoelectricity is only finding its first futuristic uses today, the phenomenon itself has been known for nearly 150 years. It was first discovered in 1880 by Pierre and Jacques Curie. While studying crystals, they found that applying pressure to materials like quartz could create an electric charge. This was the birth of piezoelectricity. Just 1 year later, in 1881, physicist Gabriel Lippmann mathematically proved the reverse effect, that applying electricity to the same materials would make them change shape. This laid the foundation for two-way applications of piezoelectric materials in both sensors and actuators. By World War I, the technology had found its first practical use: ultrasonic sonar devices, which used piezoelectric crystals to detect submarines underwater. Over time, it made its way into record players, lighters, medical ultrasound machines, and eventually into the wearable technologies and clean energy innovations that we're developing today. What began as a curious lab discovery has now become a real-world technology with the potential to shape our cities, our bodies, and even our environmental footprint. So, how does it work? Well, on an atomic level, the generation of piezoelectricity is simply a change in electric polarization. Polarization means that the material has a built-in electric bias, like thousands and trillions of tiny batteries inside, due to how its atoms are arranged. To achieve this change in polarization, a material needs to be non-centrosymmetric, meaning that the center of this positive electric charge needs to be in a different place than the center of its negative electric charge. These centers are the averages of all of the positive charges in the material and all of the negative charges in the material, kind of like a center of mass, but for electricity. The change of polarization happens when a pressure is applied to the material. This pressure leads to the slight movement of the atoms, stretching and squishing their bonds. In centrosymmetric materials, this leads to the same movement for the center of the positive charge and the center of the negative charge. Let's say they both move 1 unit to the left. But in non-centrosymmetric materials, since the centers of the positive and negative charges are different, the pressure applied on the material acts differently on each of them, leading to a change in the position of each center relative to the other. This relative change is called deformation. This causes a net imbalance of charge across the material, which creates an electric field. This field can push charges through a circuit, which is what we can use to power small devices like lighters, pressure sensors, and fitness trackers. Okay, so now we understand the how, but why does it matter? We live in a world that is increasingly dependent on gadgets like smartphones, fitness trackers, medical devices, smartwatches, earbuds, and many, many more. These devices rely on batteries. Batteries can be bulky, require frequent recharging, and their production and disposal raise environmental concerns. Piezoelectricity allows us to reduce our reliance on batteries by maximizing the energy we collect from our environment. Specifically, it allows us to utilize our bodies to generate electricity as we move. We can capture wasted mechanical energy from walking, running, or even typing and convert it into electrical energy to power our devices. It's a renewable, clean energy source that's literally always available. But what are some of the applications that actually turn this movement into power? How could this be implemented into daily life? Piezoelectric insoles are one of the most intuitive applications. Scientists and companies are developing shoe insoles embedded with piezoelectric materials that generate electricity from the pressure of each step. For instance, researchers at a university in Zurich have developed a 3D printed prototype insole that produces enough power to power small LED lights. In the future, these insoles will be able to produce larger amounts of energy, and they will be able to power larger electronic devices, such as fitness trackers or larger lights, which could allow people to illuminate their path with the energy generated by walking. Unfortunately, designing these insoles is tricky. The materials have to be flexible and durable enough to withstand constant pressure and bending, and they have to be comfortable because no one wants to walk around with heavy, stiff shoes. These requirements are not easily met with any of the natural piezoelectric materials or any of the synthetic materials we have created so far. This is why researchers are actively searching for more materials that will fulfill the strict requirements of comfort and flexibility that will make this solution viable. Wearable clothing is another idea. The idea of embedding piezoelectric materials into clothing or wearable accessories is gaining momentum. Picture a jacket that charges your phone as you swing your arms, or a fitness band powered entirely by your movements. Flexible piezoelectric films can be sewn into fabric or laminated onto skin like patches that harvest energy from the natural body movements, like bending elbows, tapping fingers, or breathing. Each of these very small motions puts slight pressure on different parts of a shirt or jacket or skin-like patch. And while these forces are very minor, they could build up over a day. A study from Georgia Tech found that these tiny pressures can currently generate 4 volts during normal arm movement, almost enough to consistently power low-energy heart monitors. This is especially exciting for medical applications, where small sensors monitoring heart rate, blood pressure, or glucose levels could run indefinitely without battery changes, improving quality of life for patients and reducing medical waste. Finally, piezoelectric technology could be implemented on roads and sidewalks. This is the most promising and realistic implementation of the technology. By embedding piezoelectric materials beneath pavement, the pressure from cars driving over or people walking can be converted into electricity. This energy can power streetlights, traffic lights, or red light cameras. The idea is already being explored by governments around the world, like France, Japan, Italy, China, and the United States. Another example is Innovatech, an Israeli company. They installed piezoelectric strips beneath a test highway that generated up to 2,000 watt-hours per day, enough to power dozens of streetlights for the whole day. But making these ideas a reality takes more than imagination. So how do scientists actually create these piezoelectric materials? And how are the devices we've just talked about, like insoles or smart jackets, engineered to turn movement into power? To turn the concept of piezoelectricity into something usable, scientists and engineers have to solve 2 key problems. What material should be used, and how should it be built into a working device? That's where things both get microscopic and incredibly creative. Designing a piezoelectric system starts with choosing or synthesizing the right material. Traditionally, that meant hard crystals like quartz or ceramics like PZT. But these are brittle. They're great for industrial sensors, but they're useless inside a shoe or a jacket. So researchers have turned to soft, flexible materials known as piezoelectric polymers, like polyvinylidene fluorine, or PVDF. These materials can bend, stretch, and still generate electricity. Creating these materials, however, involves the very difficult process of manipulating their atomic structure. Piezoelectricity only occurs when the material is non-centrosymmetric, as measured before, meaning that its internal electric charges don't cancel out. Scientists use methods like electrospinning, chemical vapor deposition, or solution casting to align the molecules just right so that when a material is pressed, it creates a voltage. But choosing a proper material isn't enough. Engineers also have to decide how to maximize deformation. That's how much the bonds between atoms bend and compress. For example, in a piezoelectric insole, the material must be placed in high pressure areas, like the heel or ball of the foot, and connected to tiny circuits that can convert and store the energy. Designers often also use stacked layers or patterned films to increase voltage output, kind of like stacking multiple sponges to squeeze more water out. In short, it's not just about picking the right material. It's about building a microscopic machine that turns pressure into power as efficiently and invisibly as possible. As technology becomes more deeply woven into our everyday lives, one thing is clear. Our demand for electricity is growing fast. And the way that we currently meet that demand isn't sustainable. Today's global energy systems still rely heavily on fossil fuels that release greenhouse gases, damage ecosystems, and accelerate climate change. But piezoelectricity offers a different vision of the future, one where energy is harvested from the wasted motion already happening all around us. It's small scale, silent, and non-polluting. Every step on a crowded subway platform, every car that rolls over a city street, every movement of the human body is an untapped energy source. Unlike large wind turbines or solar panels, which require specific locations and weather conditions, piezoelectricity systems are highly adaptable. They can be integrated into existing infrastructure, in the floors of airports, the insoles of shoes, and the seams of clothing, without any major lifestyle changes or new habits. There's also an exciting material story here. As researchers develop new flexible piezoelectric polymers and biodegradable materials, this technology is becoming more compatible with both wearable tech and sustainable manufacturing. Some of these polymers are already being made from naturally derived materials, like chitin from shellfish waste, reducing dependence on synthetic plastics or lead-based ceramics. Over time, these smart materials could become not just efficient, but fully recyclable and compostable. Best of all, this is a distributed solution. Instead of needing massive power plants, piezoelectric systems generate energy close to where it's used, right under your feet, on your wrist, or even inside your shirt. That means less transmission loss, lower carbon emissions, and smarter integration into our daily environments. Another hidden benefit of piezoelectricity is how it reduces our reliance on disposable batteries, which are a growing environmental concern. Most small electronics, like fitness trackers, remote sensors, medical implants, and earbuds, run on lithium-based batteries that need regular charging, replacement, or disposal. Globally, we discard billions of batteries per year. Many end up in landfills where they can leak heavy metals like cadmium, mercury, and lead into soil and groundwater. Manufacturing them also consumes rare earth elements and requires energy-intensive mining and processing. By powering low-energy devices through piezoelectric systems, we can reduce how often batteries need to be recharged or replaced, and in some cases, eliminate the battery altogether. Imagine a remote sensor in the middle of a forest that powers itself for years. Even modest improvements, like charging a smartwatch during motion or powering an LED indicator through foot pressure, add up over time. Every little bit of energy saved is a step away from battery dependence and toward a circular, low-waste tech future. All of this might prompt you to ask, if piezoelectricity is so promising, why don't we see it around us already? Firstly, the energy output is small. Piezoelectric devices generate relatively tiny amounts of electricity, often only enough to power low-consumption sensors or LEDs. Charging a smartphone or larger device would require much more power or much larger arrays of piezoelectric elements. Scientists are working on improving material efficiency and designing systems that combine multiple energy sources, like thermal and solar, to create hybrid systems that are more efficient. Second, for wearable applications, materials must be durable, flexible, lightweight, and comfortable. Some ceramics with strong piezoelectric properties are brittle, while flexible polymers have lower output. Creating materials that balance these properties is a major research focus, with advances in technology offering promising new composites. Even when piezoelectric materials do generate electricity, another hurdle emerges: how to store and use that electricity efficiently. Piezoelectric materials usually produce bursts of low voltage alternating current, which is rarely directly compatible with most batteries or electronics that uses direct current. This means the system needs additional circuitry to convert and store the energy, often increasing cost, complexity, and energy loss. This additional circuitry also takes up space and has mass, making wearable applications of piezoelectricity much more bulky. The good news is that breakthroughs are happening fast, and that new materials are being generated that improve efficiency and flexibility. Researchers have developed ultra-thin, flexible piezoelectric films that can conform to body contours, opening up possibilities for wearable electronics that feel like a second skin. These films are getting to be under 10 micrometers thick, or 4/10,000ths of an inch. Additionally, piezoelectric materials are up to 15 times more efficient than just 5 years ago. In the future, these advances could lead to self-powered fitness trackers that never need charging, smart clothing that monitors health and the environment while powering itself, energy harvesting smart cities where sidewalks and roads contribute to the grid, and medical devices that can run indefinitely inside or on the body. So, can movement power the world? Will our roads, jackets, and shoes become power sources in 10 years? What do you think? Thanks so much for joining me onto this journey in the world of piezoelectricity. If you enjoyed this episode, please subscribe and share it with your friends. I'd love to hear your thoughts and questions at breakthroughbroadcastconnect@gmail.com. Next time, we'll explore wearable technology for athletes designed to improve performance and reduce injury. Can't wait to share some cool insights with you.